posted with this. There were two things posted. One had IR with a few simple instructions that also go with this packet. So if we're going back to our order of operations for Spectra, the first thing that we did, all the way to the beginning, the steps, and this was again posted with the notes, first thing, get the functional groups from the IR, then get the molecular weight and the molecular formula. So the details of the chapter were those two things. That's where we're after, so let's do it. 1,500, 3,000. Tricky, ignore it. It's 80% or less. That's an enol that's isomerizing with the ketone. We don't know about that yet. There's a reason it's there, but it's not important for analyzing the functional group. That's why we ignore below 80% transmittance, or above 80% transmittance, right? What do we see? To the left of 1,500, very broad signal, CO double, not an aldehyde. Got to be broader than that and come with a neighbor. Two broad singlets. That is just an sp3CH. If it were an aldehyde, it would look like that. Okay? Not an aldehyde there. It's rarely confusing there, but sometimes you will see a little peak there that's trying to get you to pick it. All right? There might be a CO single in there. There might not be. I can't tell. Okay, that's just the fingerprint region. That CO single moves around. You can never rely on it. Let's move on to the mass spec. So I know that my molecular formula is most likely CHO. Something. Some number of those three atoms is what I'm guessing right now, but I don't know that for sure until I analyze my fractions. So if you're keeping track, what am I doing now? The next step is label the molecular ion. Looking at our list of masses, the highest mass that registers is 102. The next highest mass that registers looks to be, looking at our list here, 87. Okay, and then 74, ding, 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 that's even. That's an even mass on an assert. That's special. It's either M-18 and a loss of water, or it could be a McClafferty rearrangement. We'll check that in just a minute. Next highest mass, 71. 59. Okay, 55 is a little small there. Well, we may look at that. Notice how I'm ignoring all these small peaks in a cluster. I'm not looking at those. Those peaks are not highly probable, means they're not due to a major fragmentation mechanism that we've learned. They're due to random chance of sigma cleavage, and that's much less informative than our major alpha inductive heterolytic homolytic cleavage type mechanisms. Okay, the halfway point's at about 50. Hey, but there's the base peak. Better consider it at 43. And then anything below that, I'm not going to worry about. Okay, anything below the base peak here, at below the halfway point, whichever's lower. Okay, I don't want to think about those because they're double fragments. This one's probably the hardest one in the packet to me. Because of all the different peaks we've got to rationalize for this one. Okay? Now, what we can do at this point is see if our molecular ion makes sense. Okay, 102, it's even, that's a good start. There's no nitrogen if that's the case. And N-15 makes sense. Okay, making sure here, going to do the rest. 102 minus 74. That's a 28. Add some McClafferty, folks. Okay, 28, that screams at us McClafferty rearrangement, not loss of water. It's not 18 and it's still N-28, it's even. Okay, then, after that, N-31. that has to be OCH3. That's the only thing it can be. So we just got a little evidence of a single bond oxygen, not just a carbonyl. Okay? That's important. That's enough for me to say at 102, I've got my molecular ion. But I'm going to keep labeling these. 102 minus 59 is 43. Loss of an alkyl fragment, that's alpha cleavage. Alpha. McClafferty. Okay, loss of a fragment, that could be inductive or it could be alpha. But we know loss of an alkyl is going to be an alpha cleavage. 55. Try again. 57, or 47, excuse me, and minus 47. Okay. Then 43, 102 minus 43 is 59. So gotta have oxygen in it. Gotta have oxygen in it to be 59. There's no alkyl group that adds up to 59. 57 is an alkyl group. All right, so we've got everything labeled. As it differs from the molecular ion, they all make sense for the fragments we're used to seeing. So now we want to propose our molecular formula by either dividing by 13 immediately. Let's do that. Let's do it that way. Since last time we subtracted oxygen first, let's do it the other way. Just do 13 first. Either way works. They both work. 102 divided by 13 is 7 and some remainder. 7.846. Okay, well, let's see. C7H7. 13 times 7 is 91. So 102 minus 13 times 7 102 minus 91 is 11. That's 11 left. The remainder of 11. So we've got to add that to our hydrogens. Okay. C7H18. Does that add up to 102? Let's check. 7 times 12 is 84. Plus 18 times 1 is 102. Yes, we've added everything up right. We're good to go. That's our all-carbon hydrogen molecular formula. But does it make sense? No. Degrees of unsaturation. 1 plus 7 plus the number of carbons minus hydrogens over 2. 8 minus 9 is negative 1. That can't be right. But we knew that wasn't right because we know we've got an oxygen in there from the IR. Okay? So what we're going to do is account for that oxygen by converting a CH4 to an O. 16 and 16, the same mass. We're going to take away 1 carbon, go from C7 to C6. We're going to take away 4 hydrogens, go from 18 to 14. And then convert that to an oxygen. You're worried, check the math again and check your math. Okay? Does this make sense? Check it again. 1 plus 6 minus 14 over 2 is 0 degrees. That doesn't make sense because we know we've at least got 1 degree of unsaturation. We've got a pi bond. A pi bond from that oxygen to carbon double bond that we saw in the IR. So we know we've still got to account for a degree of unsaturation. So we've got to do something else. In our spectrum, we saw an M-31 peak. Okay? From our ethers slides, the M-31, the only thing we can have is oxygen plus CH3. 16 plus 15 is 31. There's no way to have a CO double bond bonded to a CH3 and have it weigh 31. It's got to be a single bond to oxygen. And that is evidence for our second oxygen. But you didn't need that. You could have just said, well, my degrees of unsaturation don't work out. I might need to add another oxygen. Okay, that's the other thing you can do. And check your work. C5H10O2, again, CH4 to O. Why? M-31 is OCH3. Do a CH4 to oxygen. Does this make sense? 1 plus 5 minus 10 over 2 is 1 degree. Finally, we make sense. It agrees with our IR. It agrees with our IR. It also agrees with our mass spec. That's the hardest one in the packet because you've got to find that second oxygen. Maybe I should have let you do it on your own. Okay, that actually, the folks in Atherhole would probably say you learn more from that. I think you got enough practice in the rest of the packet to at least have this be something we can look at here and do together, I think. All right, so we've got a molecular formula, but the problem says propose a structure. The problem says propose a structure. So we've got already 5 out of 10 points because we've got the molecular formula. Now we've got to get to the structure that agrees with our spectrum. That's where the fragments come into play. Fragments come into play there. So first we label the spectrum with all our peaks and our M minuses. Then we get our molecular formula, and now we go back and look at the peaks. So we know C5H10O2. Let's see if we can find something that agrees. All right, the highest fragments, the most likely fragments first. Well, we need a McLafferty. So what I would do and this is the most important part of this spectrum, is when you have an even mass fragment, you have to account for it first. You've got to explain it. It's more important than the rest of them because it's so rare. Because it's so rare, we've got to explain it somehow, M-28. To explain an M-28, there's really only a couple of ways to do that. With this compound.
Oh. That minus 28. The CL was the fragment.
A McLafferty
is it CL?
that eliminates ethene, CH2CH2,
Isn't it 28? No. Yeah,
from a propyl group attached to that
what
ketone,
I'm saying is right.
or
I think so.
an ethoxy group and an ester attached to that ketone. Those are only 2 ways it can happen. Only 2 ways, and so we've got a clue as to what we should look for. Okay? Let's go over to the side here. So M-28, we're doing our logic on M-28. If it's one of these two. Again, the McLafferty makes that 6-membered ring, 1, 2, 3, 4, 5, and 6. Back to the carbonyl with the charge. If we're seeing that, we should also see an alpha cleavage that gives you the loss of an ethoxy group. So that's 16 plus 14 plus 15, 45. Or an alpha cleavage, because there's, for alpha cleavage, remember alpha and beta away from the charge. Alpha and beta away from the charge. Or an M minus 43 for that propyl group. M minus 45 or M minus 43. So let's go back and look at the spectrum and see if we have either or both of those. If we have both of those, we're going to have to go on to the next thing to help us out. Okay, so it's a problem we're solving in a particular order. M minus 45 or M minus 43. Mechanistically, I'll show one of them. That's how we get our McLafferty. And there's our 28. The loss of the ethene, CH2, CH2. The alpha cleavage proceeds by a different mechanism, which is more, there are more examples of it in your book. Okay, you don't want to put too many things in the same place on the same slide here. But what we've really done is said, okay, do we have M minus 43 or M minus 45? Let's go back and look at the spectrum. Which one do we have? M minus 43. Perfect. M minus 43 and no M minus 45. Thank goodness. We had both. That means the other side of the molecules playing tricks on us. So M minus 43 is present, and there's no M minus 45. That means I feel pretty good about this structure of 1/2 of my compound. There's half of it right there. Well, the other half would form from an alpha cleavage of M minus 31. Let's have a look and see if that works out for us. Okay, so we like this. We pick this one because M minus 43 was present or is present in the spectrum. So then what's left? An alpha cleavage here. There's alpha beta. The alpha beta bond breaks to give us M minus 31. That compound has 1, 2, 3, 4, 5 carbons, 2 oxygens, 1 degree of unsaturation. That's your structure. Satisfies the McLafferty, satisfies the alpha cleavage requirements. Hardest one of any you'll do, this one. because it's an ester, and we had to figure out which side the ester was on. We had to figure out there was a second oxygen. Lots of things going on in this one. Had to adjust our molecular formula 2 or 3 times. Okay, anything that's more difficult than this, and we've got to go to NMR to help us, because we won't have enough information. This one, we do have exactly enough information if we know what to look for first. The order matters. Your even mass ions have to be explained first. It gives us a place to start. The more rare occurrence is something we have to get at first.